C. Ok, todo mundo pode ver a tela? Yes?
Sim.
Okay, so good afternoon.
Sim.
Today I'll talk about CPU parallelization. And the idea is to show examples of different ways to parallelize codes using Python. Explain a little bit what happens in the hardware level between the CPU and the memory, and explain the difference between some technical terms like what is a core and what's a thread. And in the last presentation, we saw the difference between the speed of the language that you can use, and basically is that the interpreted language like Python much slower than the compiled languages like C, Fortran. And when you use those wrapper techniques in Python, where you call where pieces of the Python code is compiled, it can be as fast as the regular compiled languages. And just a second. Okay, and the basically reason why Python interpreted language is much slower, it's because it needs a greater number of machine instructions to execute the same function. And I will explain this showing the memory, and this will already help us to understand this concept of CPU execution. So here just showing what so you have the source code, you compile, and then you have a machine code. So basically, this is an abstract representation of the run memory. And when you execute executable program, so when you run an executable program, what the computer does is to fill the memory address with machine instructions that will tell the CPU what it has to do for each instruction. So here we are seeing the RAM, where we have 16 slots, and each slot have a sequence of binary digits, which the commands of the code that we are running. So this is the very basic design of a CPU. So here, in this square full of things here, we have the CPU, and here we have the RAM. So what basically is happening in the computer is that the CPU works with a clock, and this clock is constantly running so that the CPU is reaching the memory, reading what's in the slots of the memory, bringing this information inside the CPU, then it decodes it, execute something, and release an output or something like that, and then go for the next cycle. So basically, when we run an executable code, what the computer does is to write the commands here, and the CPU then will access the RAM. And in this first line here could be telling us that, okay, so the CPU access this value and load it here, and then it will read this, and this could be telling us that okay, so I want you to read the value in address 1 and read the value in the address 2, and then add the 2 address and save in address 13. And this could be an example of you defining a new variable based in the value of 2 other ones. So this address 1 could represent the variable x in the code, the second one, the address of the variable y, and then you want to save a variable z here in this memory location using adding these two instructions. So this is basically what the CPU does. So we can put a big square here and abstraction telling that the CPU is this thing here. And basically what it's constantly doing is doing what they call fetch, decode, and execute. So fetch is the action of you get something and retrieve something. So the CPU in each clock cycle is reaching the run, reading some input, decode this instruction, and then execute this instruction. And when we are seeing inside the CPU, basically we have this control unit that decode this instruction, then access the structure. We have the LIU. This is the arithmetic logistic unit. This is the part of the CPU that will actually do the codes. And then we have these registers that are very fast memories inside of the CPU. But the basic idea is that we have the CPU, we have a RAM, and we have this clock here. And the CPU fetches the data on the run, decode it, execute, and repeat the loop. So Python is very, very slow, because for a same operation like this one, you want to add a value to a variable, so x equals to x plus 1. Python needs 378 machine instructions. So if you are looking here, this simple code in Python would require 378 slots of RAM memory, and then the CPU will have to access these locations 378 just to add 1 to a variable. While if you do this in C, so x++, it only takes 1 machine instruction. So this is why Python is much slower than the other languages. So now let's talk about parallelization. And the first thing is the difference of real parallelization and concurrent parallelization. So here, what Karini was talking about in the last presentation, the basic example is that you have the tasks, the task you want to do is to wash and dry 4 bags of clothes, and you only have one wash machine and 1 dryer machine. So if you put this process in each one, takes 30 minutes to run. So if you place the execution of these machines in serial, it will take 4 hours to execute. But when the dryer is running, there's nothing inside the washing machine, so it's idle. So you can use this idle time, and then you can have a concurrent execution, which means that you wash the first clothes, take out of the dryer, the washing machine, and put on the dryer. And when this is empty, you already load the second task here, and then you can, in this case, you can go from 4 hours of execution to 2 hours and 30. So this is the example of concurrent execution. And now, if you are talking about the CPU, we saw that the CPU in each clock cycle is doing the fetch, decode, and execute. So it's fetch, decode, and then execute. So this would be the serial execution. But these 3 steps are done by different parts of the CPU. So we can optimize this using a concurrent execution, because the part of the CPU that fetches is different the ones of the code and different from the one that executes. Then and then here you can optimize a lot the execution process, but you are never executing the same part of the CPU at the same times. So this is the difference from parallelization. the parallelization will be that we have 4 executions running at the same time, and while here we see we have several executions running concurrent. So this is the main difference, because in the CPU you have different parts to do each one of those tasks. And then here is an example that in some CPUs you could have extra circuits. So for example, instead of only having one arithmetic logistic unit, is that the part of the CPU that make the calculations, you can have 2 of them. And then in a single CPU, a single core having these 2 arithmetic logistic units, then you can have a parallel execution plus the concurrent one. So you're seeing the parallel and the concurrent at the same time. And this is only the case where the CPU has only one core. When in the modern computers, we will have quad-core systems, for example. And so what basically we have is that we have almost independent sets of CPUs that end up working together as one, because they have a shared mechanism to share informations and data. So this is basically what we have in a quad-core systems, where you have this 4 systems working together. So this is the basically difference between concurrence and parallelism. So here showing that the process are doing in like the dryas in here at the same time. So now let's go to the difference between cores and threads. And if you enter your Linux and you type agatop in the terminal, you'll see the screen where it shows in case of my notebook, will show 8 will be 8 processors and the use of the run memory here. So, and when I'm running a code here, so I'm running a simulation in serial, it's using only one core of my CPU. Here you see it's running 92%. And then you could ask yourself, how many cores are in my system, in my computer? How many threads? And basically here, what we have is 4 physical cores, and then for each core we have 2 threads, which results in 8 what's called logical cores. So to explain this a little further, if you go on the terminal and type ls CPU, you have a list of your hardware features, and here we can see it says we have 8 CPUs, all right? But also we have 4 cores and 2 threads per core. So now you can get a little confused and thinking, okay, but what's the CPU? What's a thread? What's a core? And this is what I'm going to explain now. So here it's a very nice image from this YouTube video here from MaxTech. What you're seeing here, it's one CPU, so this square here, that contains 4 physical cores, and it contains 1 thread per core. So the best way to think about thread is the full name of it. It's a thread of execution. So for each physical core that you have, you need at least 1 thread of execution. So the thread is, if you think the word what means in English, it's like a few. So it's a line of execution, and the processor needs 1 core at least to process the information. So for each core, you need 1 thread. So here, and this is easier if you think about very old computers. So here we have this very old computer that need these threads of machine instructions to type some output here in the paper terminal. And if you don't have this thread flowing inside, nothing will happen with the computer. So so it will be the same as the computer be in install mode. So for one core to run, you need at least one thread of information. And what is so hyper-threading, or what we see in that image of my computer with 8 cores showing? What we are seeing is the 8 logical cores, because in the modern architecture we have hyper-threading. That is when you have 2 threads per core of your CPU. So to make all the terms clear, one computer basically has one CPU, which be this integrated chip. Each CPU can have more than one core, like here 4, and each core can have at least one thread of execution, and if it's a hyper-thread computer, like the majority of computers nowadays, it would have 2 threads of execution. So what basically does it mean? So a thread, it's basically an abstract representation of the cycle of fetching machine code from the run memory and passing to the processor. But basically what you have here is a sequence of commands that the CPU the core number 1 of the CPU has to execute. So let's say it's executing this code, but then in one part of this machine instructions, it tells the CPU to wait for an input-output signal. So basically, what would be this? You have a code. You send a code to execute some calculations, then print on the terminal an answer, and then ask the user to choose one of the 2 answers given, so that the code can keep going. During this time, this thread cannot keep being computed, because it's require the input information. So in this situation, this core will be stopped. And then if we have in this thread another program that do not depend on this information to run, it will not be able to run, because it's waiting for this other code. But if these parts do not depend on this input-output information, you can put it in a second thread that will work concurrent to the first one when this first one is stopped. And this is basically what's called the hyperthreading. In this example, showing here the operational system, telling in this core first to execute this thread in blue, and then change to the thread in red. And basically, this is the hyperthreading that works with a scheduling program. And so basically, this is the hyperthreading. This is why we see 8 cores in my PC when we use Edge top instead of only 4. And another example from this dude here, he says that you can think like, if you think about the process of eating. So you need to take the food, put in your mouth, and chew the food. So the core is your mouth chewing the food, and the thread is the act of getting the food and put it on your mouth. It takes a time to get the food and put it on your mouth. So if you chew faster, then you can put the food on your mouth. If you have 2 hands or 2 threads, you can be almost all the time chewing the food. And if in this example of we are getting the food and chewing, if the amount of time that if the core computes the information 2 times faster than the time you have to get the food, then if you put 2 threads, you will double your performance of your computer, because the computer was half the time stopped. This is the case of the first example of the dryer machines. But generally, this is not the case, and hyperthreading in the, I guess, 15 years that's going around, it is estimated that improved the uses, the boost in the performance in some kind of 15%. So when you are using 4 cores to do one task, probably you get 4 times faster the execution. But when you go to 8, the amount you gain is about 15% only, because of the difference between parallelization and concurrency in threads. So this is the difference between cores and threads. And now what could be confusing is because I'm basically, seems that I'm associating thread execution with the concurrent execution, while here I'm showing that we have parallel process via process and parallel execution via threads. Also concurrency execution via threads. So now I'll explain the difference between these 2 types of parallel execution. And if you take that first example and trade that CPU, 1 core CPU for this 4 core CPU, we will see basically here the structure of the modern computers, which is symmetric multiprocessing structure. This is basically telling that all the cores, all the brains inside of the computer, all have access to the same memory. So each one of them can access the same memory. So this is how modern computers work. If you take 2 independent computers, they will have 2 independent memories, so they can only access their memories. So this will be the opposite architecture. So when you think about parallel process, what we are doing is we are running 4. Here in this example, we are running 4 independent processes, so 4 independent codes. So here you are solving a Langevin equation, here you are solving a Newton equation, here you are solving some other things, independent codes, and each one of them will run in one independent CPU. And when you run this type of process, the computer allow each of process to have only a piece of the memory, and these memories cannot share information. So the process 1 cannot overwritten things that are being written in process 2. So this is a way to have a safety management of your computer. And when we are talking of parallel threads, is that you have 1 process that can access all the memory, and then inside this process you can break it in threads. For example, here the green structure here, and then tell that instead of running this 1 process in just 1 core and then reading this sequentially here in serial, you can take all this block code in gray here, break it in 4 pieces, and each one of these pieces will be 1 thread, and then you can send each one of those threads for one of the cores. So here you have a parallelization using threads, basically doing the same thing as this one. So I'm showing this for one of the reasons I'm showing this is that show that basically these 2, depending on the situation, these 2 parallelization processes will end up on the same results. But the difference here is that this type of parallelization, the process cannot communicate the memory directly, while in threads they all share the same memory. So when you are doing parallel threads, you need to be what they call thread safing. You need to be sure that when the thread 1 is reading and saving memory in this location, this memory will not be overwritten by thread 2, because in part of the code it tells to write inside of the other memory. So this is the basically difference between parallel processing and parallel threads. And now to give nomes aos bois, names to the, I don't know how to say that in English. Then showing example of how to do each of these parallelization techniques, you have a parallel process that you can use the Python class process. You can have parallel threading, where you can use OpenMP or Numba that also use OpenMP. And you have Python threads to do concurrency. And there's a lot of confusion about OpenMP because it says OpenMP. So you think multiprocessing. So OpenMP, it must be a multiprocessing technique. But no, it's a multi-threading technique. And the MP comes from this structure here of the computer called symmetric multiprocessing, which identifies the architecture where you have one shared memory for all the things that are running. So basically, threads use SMP, thread parallelization use SMP because you have a lot of, you have different, let's say, threads running, but all using the same memory. So this is why you have MP here in OpenMP, but it's not multiprocessing, it's multi-threading. So let's go to now results and showing an example. And first, let's see example using Python process and comparing to Python threads. And I will show that we cannot have, the Python threads cannot do parallel multi-threading, but only concurrency. So this dude here is, it calls itself the Engineer Man, if you search for his channel in YouTube. And here, what he's showing here is that basically is basically the same commands structure to use Python thread library or Python process.
Can I ask a question?
Yes, yes.
Let's go back to the last slide. So what you're saying is that Python thread library, it only makes parallel threads in the same core. It cannot use multi-core at the same time. Is that it?
Yes.
Okay, thank you. Yeah, that's...
Yes.
Yes, that's it. You... Okay.
Yeah, that's it. And I will explain a little bit more, and if my answer is not correct, then you can let us know. But okay, so here, how you use parallelization in Python? You import from threading, you import the class thread, or from multiprocessing, we import process. Then the idea here, what he wants to do is execute this function calc, which makes a loop of 4 millions loops, where he makes the square root of this number. So it's 4 million square root calculations. And he will execute this using threads in Python and using process. So the idea in Python parallelization is that you need to pass a target function so to be parallelized. So it always works like that. You define a function. So if you have this function you want to be parallelized, you need to define it, and then you pass to the thread class here the target, which is the function calc. So it's basically it. So if you take this code and change, you can change this function for any function you want and see if you can parallelize it. So here the 4 in the number of CPUs. He's using all the cores in his computer, which are 36. And then he executes. He makes a for over this 36 CPUs. For each one, tell to execute the function. And then here you have some specifics, attributes that you need to run those things. Basically, you need to start each of one of the threads. Sorry, I should have explained it, that when you are using these thread classes, what you are creating here is you are is instantiating an object where one of the attributes, methods of this object is to start it, and when you start it, you start the execution of one thread. So here he defined 36 threads, and then he started each one of the 36 threads, and then in the end, you need to use this join, very important here, I will show after, which this join is telling us is that when you start doing a parallel execution, each one of the threads or the process can end in different times. So you need something to synchronize all of them so that the main code waits for everyone to stop. So when you put thread point join here, you are telling the main program here, the main thread, to wait for this thread, or in this case, since we are doing a loop over all the available threads, to wait for everyone to finish so that the code can keep running. And I don't need to explain this again here for process, because you can see it's exactly the same thing. You just change process for threads and the important technique. But when, so here he's showing the execution of the threads. And here he's printing, telling that each thread received each one of the 30, I'm sorry, I was telling 36, but 32, I guess. So each one of the 32 threads are receiving information to be computed. But if you see the CPU use here, it's only using one CPU. So one CPU and 100%. So this thread technique here, it's working in serial, while if you use Python multi-process here, you see all the CPUs firing. And the reason, because threads in Python do not work to solve this type of math problem, is because in Python threads can only do concurrency, and which is that scenario where you are, sorry for that, you are waiting for you get to a point of your code, and then you are waiting for an input-output information. And Python threads is to do this type of things. And for scientific program, this is basically it's not useful for us, because we want to use all the CPU all the time to make calculations. But when you are working with web pages and internet, a lot of times you need to wait for the input information for the user. And in these scenarios, then Python threading can be very handy. But in our case, it will simply work as a serial execution. So pure Python cannot do real multi-threading. What pure Python can do multi-processing, where you can do a parallelization process, and then there's two libraries, process and pool. And Python can do concurrency threading using import threading or import async IO. So remember that I was talking about input-output information. This is IO. So threading, it's not what we want to use in scientific programs, so basically. But when you use Numba, Python then can do real multi-threading, and the way it does is using OpenMP. So basically, Numba is it's a wrapper inside of a Python function that make this Python function be compiled in C++ and in other language level, and it has an easy-to-use option to parallelize in multi-threading that use OpenMP. So now let's talk about these two, the difference between process and pool in Python. The two ways in Python that you can do multi-process parallelization. That the one that, if you remember, is the case where each process has an independent piece of the memory to work. And here I'm showing a code of the importance of using join and how to break your computer. And when I'm talking about breaking your computer, I'm talking about you overloading your run memory until the point that the computer cannot process anything else because there is no more space to put information in the run. So the computer gets stalled and don't know what else to do. In this example, I'm using Python, and so I didn't put here the library importing lines, but are the same of that example I showed you before. And here, the only difference is that instead of having in target here that calc function, I have a default plot function. It's a plot function that I made. And what this code is doing is making a for over all the input, the name of all the input files that I want to plot. So they are 150 data that I want to make a graph. And then for each one of them, it will call the process, passing the function target here. And the arguments of the function you place on the side. So default plot has the two arguments, input data name list and system, which is it's a dictionary. But basically, what I'm showing here that each time this line is executed, instantiating one object calling P1, which will be an independent process where the target of each process will be these default plot functions, which will have these two arguments, the name, the path, and the name of the data that need to be plotted, and this other argument that doesn't matter. So this function will receive this path. Inside of the function plot function, it will load the data, will work off the data and plot the figure and export and save the figure. So nothing will come back to the main program because I'm calling a function and the function is doing everything inside of it. And then for each process that I call, I start the process. So the process is being executed by one core. And in this case here, I'm placing the join outside of the loop. And if I does that, what we'll see is all the cores of all of my computers firing 100%, and my run memory growing and growing and growing here. Here are the instance of each process running. And if you compare the before and after I run this code, we see that without the plot, we had running 131 tasks for 133 threads of execution, so pieces of threads. And after running this routine with 150 plots, we have 282 tasks. So basically, if you add 150, you get this number. And in the moment where it got stuck, and then after some time, the computer got stuck. And the reason why the computer got stuck, it's because I should have put this join command inside the loop, because the join, what is telling? It's telling that the code needs to wait for the here. The join makes the main process wait the sub-process to terminate, and then prevent the second process from starting. So when I'm placing the join here before, I'm basically telling that all these 150 processes are running one after the other without waiting for the other one to end, and this ends up consuming a lot of run memory and breaking the computer. So the solution is basically that you need to define how many cores you want to run, and then I'm sorry. In this situation here, I would not have any problem if I had an absurdly large number of run memory. But basically the idea when you are using process is that you want to pass the number of process at each time equals the number of cores you have. Because if I only have 4 cores, and I'm here sending to execute 150 process, then the first 4 processes will go to each to one processor, and they will be computing. But the next 4 will be on the line, and so on until you have this really big line all saved on the run memory, waiting to be executed. And if this line gets too big, your run explode, and then you cannot execute the code. So what's the solution? The solution is to break your process in groups. In groups in the number of processors you want to use. So here I'm defining that I will use 4 processors. And so in this case, he will probably use the 4 real ones. Then I made a 4 instead of in the 150 images. I made a 4 in 150 images divided by the number of processes. And then for each, and then I call an inside loop where I will call 4 processes at a time. So you are seeing here the J is ranging number of processes, so it's 4. So I'm basically instantiating 4 jobs, 4 processes at a time. So 4 Python plots at a time, starting them, and then I use this join so that in this manner, so that the code cannot keep adding new process until the last ones are executed. And now when you run in this way, you see that only 4 of the cores are running. But what ends up happening is that you cannot have, when they are running, you don't have 100% of each CPU running. You have something that keeps changing, basically because the way I coded here, the next 4 process needs to wait the 4 anterior ones to run. So if in this case I have a lot of idle time on my CPU, and so for this that you have the pool method, which basically controls the pool of processes, because the processes in the PC are organized in pools. In pools of sequence of processes that need to be executed. So the pool class manage this so that you don't have this idle time between each of the four plots. And you can see that it's very similar to process, the way to use. You just import from multiprocessing, import pool. Then you use create the pool object here, where you can define here the number of cores, basically, that you are using. Or actually here you are defining the number of processes that have to be executed at the same time. But since each process will go to 1 core, here I'm at the same time telling that I want to use 4 cores. And then here I don't need to use that. I can use a simple loop. I don't need to break anything, because the pool method will guarantee that despite I'm passing 150 things to do, he will only does those things for he will only plot 4 things at a time. And then once again, you need to use here, then you use to pull point close and pull point dot join. And when you do this, the difference is that when you use process with 1 core, the images you take 110 seconds to plot 150 images. For 5 cores, 35 seconds. For 6 core, 35. So this is the deeper threading that I was talking about. When you change from 5 to 6, you don't change much thing. But when you use pool, that will smartly arrange the synchronicity of how you execute your pool of process, then using the 4 cores, I can drop the time for 16 seconds. So in this scenario, pool is evidently the best option. And so now comes to the first conclusion of a way that you can easily do parallelization and very efficient parallelization with your codes using pool. What you will basically do is imagine that you can do even having a serial code. So you didn't write, you don't know anything about OpenMP, you just know how to write in serial code. But what you want to do is it's calculate a phase space. So here you're calculating a phase space for a parameter v, like velocity, for 4 values is separated. Very basically way to do multiprocessing parallelization is to open 4 terminal tabs and go to each one of the tabs and execute what you want to do. So here you are already doing parallelization using a serial code. So what here is the example. So if you just look at this image, you cannot know if I'm running one code in parallel in 4 CPUs or 4 different codes, each one in one CPU. So but this is not practical, keep open terminal tabs. That you can use pool. And the only thing that you need to do to use pool in this manner is that you need to change this default plot to a function that call your code. So basically, instead of this function execute a plot argument, you just put there that in the Python code, the function will call the system and tell your code to run with that parameter. And then you can have a very, very efficient parallelization using pool, where you can manage it very well, and without even needing to really parallelize inside of your code. And this is basically the fastest you can get. If your problem is a phase space, this is the best parallelization efficient you ever had. So here's the first conclusion of how to do a parallelization. If you have a main code in Python where you use Python processes and the class pool, then you can do this type of, let's say, phase space parallelization if any language that you want. So you don't need only to run Numba, Cython, or F2Py. You can use C, C++, Fortran, Java, SQL, anything you want, AWK. So this is the first idea of easy parallelization. And now let's see let's take the difference between the speeds using process parallelization and multi-threading, just to end the lecture. In these examples, I have a Python code. So this is a Python function. What it does, it receives a matrix, and then which is and then add each term of the matrix in this loop, and have an external loop here that makes you add all the terms of the matrix a several number of times. So if you pass a 2 by 2 matrix, you will add 4 terms here, and then you can tell the computer to repeat this loop like 1,000 times. So what I did here is to put the number decoratum JIT. You just place this line here, and then this code will be running C fast, and in this case, I think it's exactly like C fast. And then we are going to use the number option to do a multi-threading, and we are going to use the Python option to do via pool to do process and compare the times. So once you are doing parallelization stuffs and you want to use several cores at a time, you need to make sure that we are not overload your run memory. So this is just a tip here, where if you want to compute the size of the memory that this matrix will occupy in the run. In this case, it's a matrix of doubles, so each one will have 8 bytes, and then you just multiply this by size and divide by 1 billion to have this in gigabytes. And then just to show, there's these libraries here in Python, ps util.virtual memory. And with this library, you can check on the fly how much run space you have on your PC. Then you can put some conditions that the person that running your code cannot define a matrix bigger than the available run space, and then you can guarantee that the code will not break. This is a very good thing to do if you are running in a shared computer, or a cluster or something like that. So, to do a number parallel in 36 cores, so I'm using a PC that has a lot of cores. It's the same thing here. I'm using oh yeah. Sorry. That's I thought this image was wrong, but it's right. So I have this function, and now this number function, matrix number, will be the target that I use that I am going to parallelize using using pool. So the problem here is that since I'm going to use a process technique, I need to work around and break this big matrix in several pieces, because I need to pass, if I want to, I have 1 million if I have a matrix with 1 million entries, and I want to divide, and I want to do 1 million summations of each one of those entries, if I want to do process, I need to break this matrix in the number of process I want, because they cannot communicate. So you need to have all this workaround, so that in this case I need to break the big matrix in 36 other matrices that I call it a partial matrix, and then pass to each pool of the process only a partial piece of the matrix, because each process will run exactly the same function. So if I want to really speed up the code, I need to pass in 36 times. I need to pass 36 matrix, 36 smaller matrix to 36 different processors, and then retrieve this information. And all this working around, it takes time to build the code, and also to pass the information and take the information back. And this can be very troublesome, because when you are using pool, you can only use one channel inside of the PC to pass the information to the process from the main code. So when we are working with a very big matrix and want to break it in small pieces, we'll end up with several pieces that can be big, and then when we pass, this channel can be clogged, and then we end up not doing any parallelization at all. So the thing here is that when you are using pool, the best idea is that you call a function where inside of the function you will define the matrix, or inside of the function you will load the data you want to work, and you never pass a lot of data directly via process, because it's a very narrow channel that the operation system has to pass the information there. So I don't have the example shown here, but if I try to execute the pool in this way, where I'm passing all the matrix to each of one of the calls, the code will basically run like a serial one. And if you compare here with the example of the plot function, it will run very, very fast, because here I'm only passing the address, and inside the function, then it will load the data and work. So if you are if you want to use pool, you need to, it will be probably the best that the function that you are using as a target loads the data and allocates the data inside of it, and do not communicate directly to the main code. But this is kind of trouble, because if you're running a simulation, you want to call a function to execute the data and then retrieve it back. So the idea to do this is to use multithreading, because then in the multithreading, since the threading techniques allows you to share the memory, you don't have all these limitations of operation system channels to transport the information. And in Numba, it's very, very easy to use parallelization thread. The only thing that if you see here, comparing the non-parallelized Numba with this one, the only thing you need to add is a parallel equals to true. You need to import these three other libraries here, all from Numba. Then you need to use this line to define that the parallelization will be thread safe. So if you remember, I was telling about the threading can share the same memory. So this thread safe guarantee that when Numba is going to do the thread parallelization, you will not, the independent threads will not work with the same memory space. So you need to define this threading safe, threading layer. Then you just add parallel true and set the number of threads that you want here, started true, and then you execute the code. And when I try to execute this code, nothing happened, and it accused an error. But the good thing is that instead of just telling me that there was an error here in the key argument parallel true, it outputs telling me where I can solve this error. So this is a link. So if I run this code, it will not run. It will accuse an error, but it will show me what's the internet link where I need to see to fix this error. And then in that page, you have this. You will find this function here, this attribute here, which is a parallel diagnostics. The level is just the level of information that you want. So if you use level 4, it will tell a lot of things. And then if you have a number function that you don't know why it's not working, then you just use this instance here, and it will print in the screen something like that. And and then you can read all of those things, you understand what is going on and why it's not working. In my case, what was missing is that I'm using range here, so it's a Python default range function. So I put a length here, so a size, and then it makes a list with this range from 0 to this size. And when you're using Numba, you cannot use the range. If you need to tell which loop you want to do the parallelization, and the way you do this using this p range. So when that you need to import here is exactly the same thing, but the p range tells the OpenMP routines in the parallel Numba which of the loops you are going to do the parallelization. And then when I run in this way, the Numba doesn't know which of the loops it has to do the parallelization, so it cannot run. But if you just add this p range here, then Numba already knows that, okay, this is the loop that I do the parallelization, and in this case, this is the external loop that makes how many times you are adding the same matrix. And then, just by putting these things, you can have a very fast parallelization here in 36 cores, and you basically didn't need to do any work. And while if you then compare the Numba option to parallelize this one, very short, and with the pool, then with the pool you need to work a lot of things, break the matrix, be sure that your function need to define. Oh yes, here. So if I wanted to execute this exactly same function that I'm running with parallel threading of Numba with pool, as I was told you before, I will not be able to do a parallelization because in this function I'm passing a big matrix and retrieving a big matrix. So the code ends up processing in serial. But so if you want to use pool, in this case, you need that your function, you need to define the matrix inside of the function and then return only a single value, for example, the output. So if you change your function to this scenario, then you can use pool and then you can compare the speeds. But even then, you need to do much more work. You see, I need to break all those things here and be sure that everything is going to the right place and returning in the right place. While here, I just need to put parallel equals to true and p range. And then here you can see now executing the same thing using multi-processes, and you can see all the cores running. And then finally, here's the results. And okay, someone wanted to make a comment or something? This is my three last slides. Are you there?
Just comment the last slide, please.
Okay, so here what I'm doing, in this, I'm running those codes that I showed to you, and changing the number of calculations. So the control one has 9 billion. I'm sorry. 9 billion calculations. So it's adding all the elements of 1200 by 1200 matrix 6400 times. And then in this other scenario, the number of calculations is increased by 100. When in here the matrix has the same size, but the number of times the matrix is added, it's 100 times bigger. And here the matrix, it's 100 times bigger, and the number of times it's added, it's the same. So here we have 900 billion calculations. So NUMBA serial changed from 7 seconds to 700. So basically, it's increasing linearly in time with the number of calculation, which is expected. So the number of calculation increasing 100, and the time also. And now, when we do the same thing to a number 36 cores and NUMBA thread, 36 cores and NUMBA pool, we can see that using threads, despite we are using 36, these techniques end up being like 15, 16 times faster than the NUMBA serial. When we increase the by 100 number of calculations, but the matrix remains the same size, the performance maintains the same thing. So it's 14, 15 times faster than the serial one. But when the problem change where the calculations are the same, but the question is that the matrix is now 100 times larger, we see that the efficiency of the threading techniques, it's only 5 times faster than the serial one. And if we compare the thread parallelization with itself, so this is the baseline for comparison. When we increase in 100 times the calculation, in 100 the time of the calculation, the time increase linearly. But when we increase the size of the matrix, then you see that the time didn't increase linearly. It's got a worse proportional execution time. And now with NUMBA pool, 36 cores, we see that comparing to the serial, in this first scenario, the code runs 7.5 times faster than the serial. In the second one, the code runs almost 30 times faster. But when we go to the scenario where the matrix is larger, it will only be 3 times faster than the serial, even though we are using 36 cores. And then we can also compare the difference from threads and threading and processing, parallelization, where you can see that for a small matrix, but that you want to repeat the same calculation several times, the processing technique will be 2 times faster than the threading, and almost the 36 times faster than the serial that we would expect for 36 cores. But when the problem involves a larger matrix, which means that each of the chunks that are being computed in each process is bigger as well, you see that pool ends up being half the time faster than the NUMBA 36 cores. So this is basically is the conclusion of it. So the takeaway message is that we didn't have time to discuss OpenMP, but NUMBA parallel is basically it. It's used OpenMP. C, C++, Fortran, Python, F2Py, NUMBA, they are all similar. There's no reason at all to not try Python or NUMBA if you do Python, because Python is basically written in Python, and NUMBA you just need to add a decorator inside of the function. And Python F2Py in parallel OpenMP gives you more control than NUMBA. And what would be for me the ideal algorithm is to have a multi-process pool based one to launch a phase space problem so that you can run serial codes in several cores. And when you are implementing your code or developing your code, you have an internal multi-threading using OpenMP or Numba parallel, so that you can boost the execution of those small tasks when you are developing a code. The use of multiprocess pool is good for also for external outputs like plot functions. So you have a very expensive plot function in the end of your code, you can use multiprocess to speed up. And when you're using multiprocess, especially pool class, you need to try to pass as many information to the method because of the OSPipe limitation. And know if your code is a row major or a column major. It's the case of Fortran and C is basically the way they allocate in real memory. And if you want to be very precise when doing optimizations, you need to know what the compiler you are using. You need then to search about stack use, heap memory use, predictions, and default optimizations of your compiler. And that's it. Thank you. Gracias. Obrigado.
I think we can